finish up with slant asymptotes, as well as pulling together all the different pieces of horizontal, vertical, holes, and slant asymptotes, all together utilizing one function at a time and going through the process of each piece. But I wanted to start with a couple of word problem type examples that are going to utilize either vertical or horizontal asymptotes to get us started today. So let's look at this first example. It says that a mathematical model for the population P, notice that P is in thousands, of a certain species of bacteria, T days after it is introduced into an environment, is given by this function, where time is between 0 and 5 days. So in the graph below, it is significantly larger than our domain, but I wanted to show you what the picture would look like. Let's find and interpret what is P of 0, excuse me. Well, P of 0 is representing population when we are at 0 days. We can then evaluate our function at 0. So 100 over 5 minus 0 squared is 100 over 5 squared, which is 25. So 4. And remember, this represents P as is in thousands. So this represents 4,000. This will be the initial bacteria introduced to a certain area or a certain environment at 0 days, so the initial population. When will our population reach 100,000? Also, when we are looking at 100,000, our population is in thousands, so this would be the same as finding P of T. When will that equal 100? Since 100 in this instance is the same as 100,000 because we are in thousands. So to do this, I'm just going to do my equation over here. I want to know when is P of T 100 with my function here. So it's just to be some algebra in order to solve. I'll multiply both sides by 5 minus t squared. Then I'll divide by 100. I can then take the square root to eliminate my square. So 5 minus t will equal plus 1. It will also equal negative 1 since the square root of 1 is plus or minus 1. I'll have to subtract 5. So 1 minus 5 and negative 1 minus 5. So negative 4 and negative 6 so far. Also, I'll have to divide by negative 1. So t will have to equal 4 and t will have to equal 6. Notice that when I have 4 and 6, one of these is not in our domain, specifically 6. 6 is not in our domain of between 0 and 5. So the answer would need to be 4. This tells me it takes 4 days then for the population of bacteria to reach 100,000. Part C is asking us to determine the behavior of our function as t is approaching 5 from the left-hand side. So I've chosen values of 5 that are approaching 5 from the smaller side of 5. So 4.9, 4.999, etc. So as t is approaching 5 from the left-hand side, P of t is approaching infinity. As we can see, our numbers are getting larger and larger. Physically, this means that the population of bacteria is increasing without bound as we are nearing 5 days, which cannot actually happen. For this reason, t is equal to 5 is called what we would call a doomsday for this particular population, since there is no way any environment can support an infinite many bacteria. So shortly before time is 5 days, the environment would have to collapse. Let's go to slide 2 where we can look at another example. Here we're looking at the number of students and at a local college who have had the flu in T months after the semester begins can be modeled by this function where time in months is greater than or equal to 0. Find and interpret n of 0. So we're looking for the number of students at 0 time which would have the flu. We can then substitute 0 into our function and evaluate. So n of 0 would have to be 500 minus 450 over 1 plus 3 times 0, or 500 minus 450. Well, 450 would be over 1 plus 3 times 0, and 1 plus 0 is still 1, so 450 divided by 1 is still 450. 50. This tells us that at the beginning of the semester, so when time has not passed, so the initial amount of students would have to be 50, would have the flu at the beginning of the semester. Our second question is asking us how long will it take until 300 students will have the flu. At this particular instance, we're looking for how long will time take for us to reach 300. What we can do at this point then is substitute 300 in and solve for time. So 300 is equal to 500 minus 450 over 1 plus 3t. Subtracting 500 from both sides, we'll have negative 200 is equal to negative 450 over 1 plus 3t. We will need to multiply both sides by 1 plus 3t so that we can eliminate the denominator on the right-hand side. Dividing then, we will distribute, not divide, distribute. So negative 200 minus 600t is equal to negative 450. Negative 600t would then be equal to negative 250 when we add 200 to both sides. T is then equal to positive 250 over 600, or reducing our fraction would be 5/12 months. Well, we aren't even reaching a whole month. We are just under half of a month. So we could say that it would take about 13 days, depending upon the number of months and depending upon which month the school starts. So we could say that after about 13 days, there would be 300 students who would have the flu. Notice now we have a horizontal asymptote with respect to this particular problem. So in part F, it's asking us to determine the behavior as t is approaching positive infinity. So when we're approaching, time is getting larger because in this particular situation, time can't be negative. We only can move forward in time. We can see that it is approaching 500 also by looking at our table as our x values are approaching 100. Our y values are approaching 500, and they're approaching 500 from the bottom side, so from the lower side. So as t is approaching infinity, we can say then that the population is approaching 500 from the bottom side. So as time goes by, only a total of 500 students will have had the flu. Let's move to slide 3 where we can talk about slant asymptotes. It says that the line y equals mx plus b, so it's a linear line where our slope cannot be 0, is called the slant asymptote of a graph. When y is equal to fx, if x is approaching negative infinity or positive infinity, then f of x is approaching mx plus b. So let's actually determine what the slant asymptote is. First of all, it has to be written as a rational function, p of x over q of x, where the degree of p has to be exactly 1 more than the degree of q. When that happens, then the graph of our r of x has a slant asymptote where it is the quotient obtained when we divide p of x by q of x. So in our first example, it's asking us to find the slant asymptote of the graph of the following function if it exists, and then verify using a graphing calculator. I can see that my graph probably would have a slant asymptote just on the direction with which my red lines are moving. Also, I can see that x squared is exactly 1 more than x, which is q of x in our denominator. So we can certainly utilize, in this instance, it's going to be great to utilize long division, because sometimes our polynomials aren't written where we have a binomial as the divisor. So we're going to practice our long division skills so that we can find the quotient after we divide, because that quotient is what's going to be our slant asymptote. So I'm going to start off by taking x squared minus 4x plus 2, and I'm going to divide that by negative x plus 1. So notice how I wrote it in descending order. And we're going to utilize our long division process. I have negative x. I want to make it look like x squared. So negative x times negative x would give me positive x squared. I know then I need to multiply that by everything on the left. So negative x times negative x is positive x squared, and negative x times positive 1 is negative x. Before we go any further, we do know that we need to subtract this. So this will turn to a negative x squared, and then we'll have positive x. When we go ahead and simplify by addition, I see that our x squareds create a 0 pair, which eliminate, and negative 4x plus 1x is negative 3x plus 2. At this point, we can continue because I have an negative x, and I can multiply it by something in order to reach negative 3x. I can multiply negative x by a positive 3 so that I can obtain the negative 3x when I multiply it by everything on the left-hand side. By doing so, I'll now have negative 3x plus 3. Also remember, we are going to subtract. So when I subtract, my negative 3x turns positive, and my positive 3 turns negative. Actually going through with the subtraction, we have a 0 pair with negative 3x plus 3x, and 2 minus 3 is negative 1. This is our remainder, but it doesn't matter. This part here, this negative x plus 3, this is the slant asymptote. When I'm looking at my graph, if I wanted to graph this, here's positive 3 and my slope is negative 1 over 1. I see that my graph does certainly fall in line with this slanted asymptote as an asymptote that we're trying to avoid. Also, as x is approaching negative infinity, so as x is getting more negative, my y values are approaching my slant asymptote from the bottom side. So we are approaching from the bottom side of that slant asymptote. Also, as x is approaching positive infinity, so as we're getting larger, our function f of x is approaching the slant asymptote. This time we're approaching it from the top side, on top of the slant asymptote. Let's move to slide 4 and we'll put it all together. We'll take a look at the domain. We'll identify any vertical asymptotes, any holes, horizontal asymptotes, and if any slant asymptotes exist. Our first example, I have x cubed plus 2x squared plus x over x squared minus x minus 2. And on the far right hand side, I do have the graph of our function here. I'm first going to start off by writing the factored form and factoring, because that's what's again going to tell us of the vertical asymptotes and if we have any holes in our graph. I see in my numerator that I am able to take out the greatest common factor of x, which will leave me with x squared plus 2x plus 1. And our denominator will stay the same, that does not have a greatest common factor. I then will find two values that multiply to 1 and add to 2 for my numerator. And 1 times 1 seems to work. So our factored form of the numerator is x times x plus 1 times x plus 1. Our denominator then I want to multiply to -2 but add to -1. So -2 times +1 works. So its factored form is x minus 2 and x plus 1. There are two places with which x cannot be. X cannot be +2 and -1, since if I substitute those values or set them equal to 0, we will end up with two values, 2 and -1, which our denominator would be 0, and we know that that cannot happen. So our domain comes from -infinity to -1. We're going to skip over -1 to +2, skip over and go from 2 to +infinity. At this point, we can determine what any vertical asymptotes we are by simplifying. I have a common factor which we can simplify. So our only asymptote is at x equals 2. So x equals 2 is a vertical asymptote, and I can see that that is in fact true of my function here. Also, because we crossed out the common factor, there is going to be a hole at x equals -1. We know we can find what that value is by substituting -1 into the simplified version of our graph or of our function after we have eliminated the common factor. We know that -1 plus 1 will be 0, so anything else will give our solution 0. So at -1, 0, so right about here, there will be a hole in our graph. Looking at where our slant asymptote would be, here's +3, and we're going up 1, over 1. We can see that's going to get super close if I was more accurate with my drawing here. So to look at this, as x is approaching -infinity from the left-hand side, we see that our function is approaching x plus 3 from the bottom side of the slant asymptote, since it's coming up from the bottom here. Also, as x is approaching +infinity, so as we're getting larger, this time our graph f of x is approaching the slant asymptote from the top side of x plus 3. Let's try another. X cubed minus 3x plus 1 over x squared plus x, an interesting graph to take a look at here. Notice in our denominator we have a quadratic. So it doesn't matter what we will substitute in for x, it will always be positive. So in this instance, our domain is all real numbers. I also see when I look at my numerator that I can't factor anything from the numerator to simplify. And since I'm not simplifying, I'm not going to have any vertical asymptotes. Similarly, I'm not going to have any holes in my graph. Since I'm not able to cancel anything out, there will be no holes. We may have a horizontal asymptote, but we have to look at our exponents. The exponent of 3 is greater than the exponent of 2. So because the exponent of p of x is greater than the degree of q of x, then there is no horizontal asymptote. But because 3 is greater than 2 by exactly 1, we will have a slant asymptote. So to find what that slant asymptote is, we will take x cubed minus 3x plus 1 and divide it by x squared plus 1. I have x squared. What do we need to multiply x squared by so that we get x cubed? We'll multiply by x. So x times x squared gives me x cubed, and x times 1 is positive x. Notice how they just so happen to line up, but we would want to line them up where we have an x squares under x squared, x's under x's, etc., so that we combine like terms appropriately. We know we're going to subtract, so this turns to negative and this turns to negative. X cubed minus x cubed creates a 0 pair, and negative 3x minus x gives me negative 4x, and we can bring down the 1. Notice that we're starting with x squared. I cannot multiply anything by x squared to obtain negative 4x, so at this point we're done. So the slant asymptote is y equals x. It is possible for the asymptote to go through our graph, so don't be alarmed. Unlike vertical asymptotes where it gets really close but never touches, that is not the same with slant or horizontal ones. They certainly can cross through our function itself. So when I'm looking at 0 and our slope is 1 over 1, notice how that our graph certainly gets closer and closer to this slant, even though it does go through the graph itself. So let's take a look at as x is approaching negative infinity with our slant asymptote. When that happens, f of x, our function, is approaching our graph of x from the top side of the slant asymptote, and as x is approaching infinity, this time our function is approaching our slant from the bottom side of the slant. So it's approaching from the bottom, here it's approaching from the top side. And our last example, we have 4x over x squared plus 4. Similarly to the last example, it doesn't matter what I replace x squared with, it will always be positive. So there will be no instance with which our graph has a 0 in the denominator. So our domain is all real numbers from negative infinity to positive infinity. Similarly, there will be no vertical asymptotes because there are no places we need to avoid in our denominator. So there are no vertical asymptotes. Also, when I look at my numerator and denominator, I'm not canceling anything. There's no common factors that we're able to eliminate. So because of that, we will have no holes in our graph. When we're looking for a horizontal asymptote, here I have 1 which is less than 2. So when the degree of P is less than the degree of Q, y equals 0 will be the horizontal asymptote. So this line here, and we can even see that it's getting closer and closer to y equals 0. So as x is approaching negative infinity, so as we're getting negative, our function value is approaching 0 from the bottom side of 0. As x is approaching positive infinity on the right side, our function itself is approaching 0 this time from the top side of 0. When I'm looking at the slant asymptote, there is going to be none because the degree of the numerator must be exactly one more than the degree of the denominator. In this case, it's the other way around, so there is no slant asymptote. So this concludes lessons 4.1 and 4.2, graphing rational functions using a variety of methods, but I certainly encourage you to utilize the graph so that we can identify these pieces and visually see what's happening.